I'm Jayant, and today I'm going to talk to you about a library that we've developed for doing structured prediction with deep neural networks. This library makes it really easy to express, train, and make predictions with these complex machine learning models. We use this at Microsoft Semantic Machines for a bunch of different models, and we've really had good success with it. So I'm excited to talk to you about this today. And what I'm going to do is I'm just going to spend a couple minutes explaining what the problem is that we're trying to solve with this library, because I know it's a little bit jargony if you're not in the machine learning space. And then I'm actually going to just kind of start coding up some examples, and we'll kind of build our way up to kind of a cool demo at the end. Okay? You can see I brought my keyboard, so I'm ready to go. Okay, so just to, whoop, don't do that. There we go. Okay, just to motivate the kinds of problems that we're trying to solve in this talk, let's consider the problem of converting from natural language into a computer program. Can you guys see this slide? Is this good? So this is kind of a machine learning problem that you can imagine that any sort of digital assistant has to solve, right? If you're like Alexa or you're OK Google or something like that, right? Someone gives you a command and you have to figure out what to do. And how do you think about what to do? Well, it's a program that you need to run to do the thing that the user wanted. Okay? And this is a hard machine learning problem compared to something like classification, which you may have seen, for two reasons. First of all, the output space is very large. The set of computer programs is infinite, right? So you kind of have to pick amongst this infinite set of outputs. The second reason is that the space has complex structure. So you can't just generate any sequence of symbols and have that be a valid program, right? There's things like type constraints, which you need to satisfy when you're generating the output in order to get a well-formed program. And these are the two characteristics of structured prediction problems. They have a large output space with complex constraints. Okay? And so our goal is going to be to train machine learning models for problems like this. And we're actually going to build a demo of exactly this problem. Okay? So I will show you that. We're not going to do sort of the full assistant domain, but we're going to do a little natural language calculator. Okay? So let me just show you what that's going to look like. Oh my god. Okay, so can you see this? How do I make this bigger? Does anyone know? Not like that. Well, okay. I tried sort of the normal thing. Okay. That's not good. Well, okay. If someone can figure out how to make this bigger, I'd really appreciate it. But for now, we'll just run with this. So here's the calculator that I have. And you can type in something like, what is the average of 8 and 4? And it actually computes the answer to the question. And it also produces a computation in sort of a prefix notation, which I'll explain later. And it produces a probability for that. So in this talk, we're actually going to work our way up to building this model. Okay? Okay, so just coming back to structured prediction. The other thing I want to say just about this briefly is that there's many kinds of structured prediction problems. It's not just this language to code one, okay? And each of these structured prediction problems has a different output space that you want to think about. So for example, in this problem of syntactic parsing, the output space is the set of all trees that span the sentence. And our goal with this library is to develop a library that makes it really easy to build machine learning problems for machine learning models for any kind of structured prediction problem with any kind of output space. Okay? And we've developed a library. Oh my god. We've developed a library for this problem that we call probabilistic neural programs. And a probabilistic neural program basically combines two different representations into one library. The first thing is it has a representation of a structured output space, which is basically a probability monad, if you know what that is. If you don't worry about it. I'll explain it. The second thing is that it has a library for expressing neural networks. And what's important about this library is that it allows these two components to interact. So the neural network is actually going to be able to assign the probabilities of the structured output space. And then the path you take through this output space is actually going to define the neural network itself. And this interaction is what lets us express these structured prediction problems in a very natural way. So if you've seen other machine learning libraries like TensorFlow, they kind of just do this half of the picture. And if you've seen things like probabilistic programming languages, they do this half of the picture. And ours is the only library that really combines these things together. And we'll see that that makes a very natural representation for the kinds of problems that we want to solve. OK, so that's basically the end of the intro part. I'm now going to start doing some live coding. And I'm going to do this in sort of 4 chunks. The first thing I'm going to do is I'm just going to show you how we can represent some simple probability distributions in PNP. Then I'll show you how we can actually train these probability distributions so the probabilities are estimated from a data set. And then finally, well, two things. I'll show you how you can put neural networks into that process, and then I'll show you how we can assemble the demo. Okay? So let's get started. Okay, so let me just get this set up. So, okay. To express probability distributions in PNP, there's basically two ways to do it. And to think about the first way, let's define a probability distribution that represents flipping a coin. Okay, so I'm going to make a function which takes a probability. And this is going to return a, sorry, this is a def. Coding in front of a crowd makes me nervous. Okay, so this is going to be a function that represents a, wow, let's put that in the middle of the thing. Okay, that represents flipping a coin. And whenever you see a P and P of x, think about this as a probability distribution over things of type x. Okay, and we can define this in terms of this function called pnp.choose, which basically just represents a probability distribution over a list of things. So I can give it true and false, and I can give it the probabilities that I want. So true will be probability, and this will be 1 minus probability. And I'm done. This is now a probability distribution. So let's see what happens if we print out this distribution. OK, so if you print out this distribution, it's this line. You can see we just get some crazy thing. The reason we get a crazy thing is because PNP is a lazy representation of the distribution. Remember, we're trying to represent these like infinitely large distributions. So we can't actually enumerate all the outcomes and assign them probabilities. So if you have one of these lazy representations of a distribution, the way you go from that to probabilities is you run inference. So you can think about inference as basically just exploring parts of the distribution using some strategy. And right, it's sort of like there's a tree of executions. You explore it in some way. So there's many different inference algorithms you can run. You can do like sampling. Sometimes there's dynamic programs depending on your model. In our case, we're going to do a sort of simple search, okay, just for this talk. So if we run inference on this probability distribution, you can see we get what we'd expect. We get false and true with sort of 50-50 probability. OK, so this is obviously a simple distribution. The second way that you can build probability distributions is you can compose other distributions together. And PNP is a monad, so you can do it using flat map or for yield. So let's define a distribution over 2 coin flips. We can just do flip. Let's say they're different. And I'll just return a tuple of the 2 flips. Let's just comment this out. OK, so you can see here we get sort of the distribution you'd expect for flipping 2 coins, right? And the 2 different outcomes of the 2 different coins. OK, now these 2 primitives can be combined in powerful ways to make much more complicated distributions. So to show you that, let's define a binomial distribution. So a binomial distribution is I'm going to flip num coins, each of which comes up heads with probability. And it's the distribution over the number of heads that I got, right? So it's a distribution over integers, as you can see right here. And the way we can do this is we can define this as a recursive function. So we can say if I'm flipping 0 coins, obviously the answer is 0. And pnp.value just puts the thing into the monad. Otherwise, what I'm going to do is I'll flip num minus 1 coins. And I'll figure out how many heads I got there. Then I'll flip my current coin. And then if the current coin is heads, then I'll return the count plus 1. Otherwise, I'll just return the count. Right? So I'm just adding up the number of heads that I got. And we can run inference on this guy. Let's say we flip 5 coins with probability 1/2. And let's comment this out. OK, so you can see here, again, we get sort of the distribution that you'd expect. OK? Now, I said that we'd be using these probability distributions to kind of represent the output spaces of our structured prediction model. And I'm going to show you how we can do that right now. And the way I'll do that is I'll actually build the output space of our natural language calculator. So conceptually, what do we want to do? We want to produce like an arithmetic expression, right? So we can think about that as like a tree, something like this, right? But instead of like having a data structure for trees and stuff, just for this talk, to make it simpler, I'm just going to generate a sequence of operations like this. So it's just a prefix traversal of that tree, okay? And one thing you have to watch out for, though, is not every sequence of operations is legitimate, right? So this sequence of operations isn't well formed because there aren't enough arguments to the operations, okay? So we just need to define a distribution over these sequences of well-formed operations. And to do that, let me just copy paste in a representation of an operation. It's not super interesting. I'll copy all this. OK, so I've just defined this thing called an op. It's just a type unsafe wrapper around a Scala function. And it has a name. It has the number of arguments that it expects, the arity. And then it just has a function that will call to evaluate it. These are just helpers for making some operations. And this just makes the pretty printer work, so ignore the implicits. And then I've defined some operations. So I've defined the numbers 1, 2, and 3. And then I've defined addition and multiplication. OK? So given these operations, let's define our distribution over these arithmetic expressions. Now, to a first approximation, what I want is just a distribution over sequences of ops, right? So something like this. And one way I can get that is I can just pick an op. This just means choose with uniform probability. And then I can generate the rest of the sequence. And then I can do something like this. OK, so this has two problems. The first problem is it obviously doesn't satisfy our well-formedness property, because I'm just picking the operations at random, right? The second problem is all the sequences in this distribution are infinitely long. So this will never finish, no matter what you do, right? So I'm going to solve both of these problems by just tracking sort of where we are in the tree. And the only thing I need to track for this is basically how many expressions, like complete expressions, I need to generate before I'm finished. So I'll just make an argument called remaining. And basically, if I don't need to generate anything else, I can just stop. Otherwise, what I can do is I do the same thing I'm doing here. And I just need to figure out how many new arguments I need. So for this, the way to think about it is I've generated an operation, right? So I'm going to subtract 1 from the remaining thing, because this operation is being fed into something from before, right? But the operation I generated might itself have arguments. So I need to generate all of those in the future. And then I just need to pass this down. Another way you can think about this remaining thing is I'm just tracking like the size of the stack of like the sort of things I need to fill in for the tree. And I'm just tracking the count instead of tracking sort of explicitly what needs to get filled in. OK? So
Line 1 of 3.
Sorry, say that again?
Line 1 of 3. Error, not equal. No.
Error?
Error.
Oh, no, because this is just this isn't in the monad. It's just a number. Yeah. OK, so let's see what happens if we run inference on this expression. I need to pass 1 here because I want one guy. OK. So we ran inference, and you can see here we get some huge list of these expressions, right? And I'll point out 2 things. First of all, inference didn't run forever, right? So there are arbitrarily long sequences of operations in this distribution, OK? But because inference is approximating, like it's doing an approximate search of this distribution, it doesn't take infinitely long. The second thing is just, if you look at these lists, you can see that they are, in fact, well-formed lists, right? Like every operator has all the arguments that it has, or it needs. So this is how we're going to define basically the output space of our structured prediction model. And I'm actually just going to copy paste this code later to do the actual modeling, OK? OK, so that's sort of the end of this probability distribution unit. I've basically shown you how you can define probability distributions in PNP, basically in terms of non-deterministic choices and composing those together. Now, throughout this part of the talk, everything has been using sort of probabilities that I've specified statically as like arguments to these functions, right? But when we're doing machine learning, we really want to like learn those probabilities from a data set. So in the next part of the talk, I'm going to show you how we can basically learn those probabilities using data. Okay, that's the training portion. And for this, I have a new app. Oh. Okay, so to define a trainable probability distribution in PNP has 3 steps. The first thing you need to do is you basically need to allocate some model parameters. And these are just numbers, just think about them as a collection of vectors and matrices, what have you, that are going to get optimized by training to fit your data set. The next thing you need to do is you need to define your distribution in terms of these parameters, okay? And then once you've done that, you'll be able to call some generic training operations that will fit the parameters using data. So we just have to do those 3 steps. And to do those, let's do a very simple example of training a coin flip, okay? So I'm gonna add some parameters. Each parameter has a name, which we can use to refer to it later. And it has a dimensionality. So this is like the dimensionality of its matrix or a tensor. I'm just going to make a 2-dimensional vector because we're just going to have a probability of true and a probability of false. OK. So this is step 1. Step 2 is to make our define our distribution in terms of these parameters. And previously, I told you that this like PNP Boolean is a probability distribution over Booleans. Well, actually, it's a function for model parameters to probability distributions over Booleans. So implicit in this definition is a dependence on some model parameters. Okay? So whenever you're within the PNP monad, you can get these parameters and you can basically do arbitrary neural net operations on them if you want. And the way that you do that is you just do this kind of funny computation graph thing. So I could put this in a for yield, but our neural net thing wants the computation graph to be an implicit parameter, and this is the best way to get that to work in Scala. But basically, the computation graph is a container for the parameters and then some other neural network stuff, which we'll see in a moment. OK, once I have this computation graph, I can just call my thing that I did before, this choose thing. I'll give it the same list of outcomes. And then here, instead of hard coding the probabilities, I'm just going to get those model parameters and put them in. So this thing has a method, which lets me look up the parameters by name, and I just put them into the call. I need to do one more thing, which is these parameters are between -infinity and infinity. So to make it a probability distribution, I just need to normalize them, which I can do with this, this guy. So this just makes it a probability distribution. OK, so now I've defined my probability distribution in terms of my model parameters. So now the last step is we want to train this distribution. So let's make some data. Let's say I flipped 3 coins and they came up true, true, and false. From this data set, we need to make some examples that the training system expects. And the way that we think about a training example in PNP is it's basically a combination of 2 things. So there's this PNP example. It's a combination of the distribution over all the things that could have happened, which is just a distribution. So you just give it a PNP. And then it's what actually happened. So here we got true or false based on which data point this is. And once I have these examples, I can just train the system. I'll show you what this training method does in a second. It's basically just setting up various optimization parameters. And just to show you that this works, let's print out what happens here. Let's say before training. So, oops. What am I in? OK, so before training, you can see we got some sort of arbitrary probabilities here. This is because when we put the parameters in the model, they're initialized to some random numbers. OK, so we just get random numbers out here. After training, you can see that we get sort of the 2/3 true, 1/3 false distribution, which was actually exhibited in our data set. OK, so this just shows you that training is working. Now, there's 2 things I want to do at this point. The first is you might look at this and say, OK, this is trivial. I could just count the number of trues and falses, and I could have got those probabilities. And that is true in this example, but that won't be true once we start building sort of more complicated models. So we actually need some sort of explicit optimization process. The second thing I wanted to do is I wanted to show you this training method, just to show you that I'm not hiding a bunch of code from you. Basically, this is just configuring how we want to do the optimization. So like we set up sort of an objective function, which just measures the distance between the distribution and the label. And then we sort of set up like how we want to do it. So we want to use stochastic gradient descent as the optimizer. And there's things like numbers of cores and stuff like that. So it's just sort of configuration parameters that go in here. It's not a complicated method. OK, so that's the end of the training part of the talk. Basically, here I've shown you how we can train these probability distributions by defining them in terms of model parameters and then using some optimization algorithms. In the next part of the talk, I'm going to show you how we can sort of define more complex distributions that actually use neural networks instead of sort of just having two parameters for true and false, right? And here I'm actually going to use some real data, OK? So if I just run this app. So here I'm going to use a sentiment analysis data set just to show this on a real problem. So this is a movie data set where basically each training example is a sentence from a movie review. And it's been annotated with a 1 to 5 sentiment score from very negative to very positive. So these are just 10 examples from the data set. And there's about 11,000 examples total. OK? And what we're going to do in this part is we're basically going to train a system to take this sentence and predict the sentiment score. OK? So basically, what we want to do is we want to fill in this predict sentiment function, which I've conveniently written for us. OK? And basically, you can think about this as a classifier, right? I take a sentence, and given that sentence, I'm going to return a sentence-specific distribution over sentiment labels, right? And note that the distribution that we return needs to depend on the sentence, because some sentences have positive sentiment, some have negative sentiment. And the way that we're going to build this model is we're going to use a sort of encoder classifier architecture. So this is sort of a very traditional neural network for solving this kind of problem. Basically, we're going to have an encoder which takes the sentence and produces a vector. OK? And then that vector we can just treat like a feature vector for the sentence. So we can just build a linear classifier on top of it, and then we'll be able to train the whole system. OK, so let's build this model. So we need to get our computation graph again. OK, so the first thing I'm going to do is I'm going to run the encoder. I've already written the encoder. I'll show you what it does. It's like 20 lines of code. It's just a little bit annoying to write in front of everyone. And then once I've gotten my sentence vector, I want to predict a label. So what I'm going to do is I'm just going to call choose. And here are the distributions over the sentiment labels. So the sentiment labels are, let's see, very negative, negative, neutral, positive, very positive. Right? So it's a distribution of our sentiment labels. And here, I'm just going to build a little linear classifier. So I have the sentence vector, and I'm going to multiply it by some a parameter matrix. So this will be basically labels by the dimensionality of the sentence vector. OK, so this is just a linear classifier on top of our sentence vector. And I need to do the thing to make it a probability distribution again. And I'm going to return my label. OK, and that's our sentiment classifier. So I need to do one thing, which is I have a model sitting around here. And I just need to put these parameters into it. So there's 5 sentiment labels. And the sentence vector is 100-dimensional. OK, so once I put my parameters in my model, I can now train the system in exactly the same way that I trained my coin flip. So I have some data sitting around. Let me make some examples. So this is basically sentences paired with the label. And I'm just going to do the exact same thing I did before. And I can train this. Oop. And I also wrote a little thing so we can interact with it instead of me hard coding everything. So let's train this. And this takes like maybe 15 seconds to train. So while it trains, let me just show you what the encoder does. So this is the code for the encoder. For those of you who are familiar with neural networks, this is a continuous bag of words encoder. Basically what it does is there's a vector for every word that it knows about. And it just splits the sentence into words. It finds all the vectors for each word in the sentence and then just adds them up. Okay? It's a fairly simple network. There's just a little bit of bookkeeping you have to do to figure out what words I know about. And if I see a word that I haven't seen before, what should I do? So there's just a little bit of bookkeeping up here that you have to do. OK, so the system has trained. And we can now try typing in some stuff. So like, great movie with wonderful actors. And you can see we get classification. So it's very positive with high probability. We can also try, I don't know, worst movie of the century. You can see we get a very negative score with probably 49.6. OK? So this is sort of an example of how we can train these neural networks with this PNP system. OK. Let's just get rid of these guys. OK, so that's the end of the sort of neural network portion of the talk. And the last thing we have to do is we just have to assemble these three pieces to build the demo system. Now, hopefully, at this point, you can kind of guess what I'm going to do to build this system. What I'm going to do is I'm just going to copy paste that expression code we saw before. And I'm going to feed in some neural networks to score each choice. OK, and that's it. We're going to end up with a fully trainable system. OK, so let's do that. OK. So again, here I have a thing, but I forgot what it was called. OK. OK, so basically we want to fill in this method here, right? We want to be able to take a sentence and produce that distribution over operations. And I will copy paste this expression code. So I've already pasted all the op definitions and stuff into here, so we don't have to do that again. And oh yeah. So the way that we're going to fill in this method is we're again going to use an encoder kind of architecture, but it's slightly more complicated because in the expression thing, we now have to make a sequence of decisions. And so we're going to use a special neural network for that that's called an LSTM. And the way to think about that is it's basically just a thing where you give it a vector, and it'll give you a vector and a new state. And then you can give that new state a new vector, and it'll give you a new vector and a new state. Right? So it's kind of like a stateful thing that you advance by providing vectors. So what we're going to do is we're basically going to take this LSTM. We're going to use its first vector to score our decision over operations. Then we're going to give it a vector and then use the next vector to score the next operation, et cetera. So to do that, all we have to do is basically thread the LSTM through this function. So I'm going to call it a scanner because our data structure is called a scanner. And name a computation graph. OK. And here, basically, I just need to replace this choice over ops with I can get the vector from the scanner. So think about this like the sentence vector, except it gets advanced, right? And I'm just going to build a linear classifier on top of it again. And again. OK. So now I've scored my current decision. And the next thing I need to do is I just need to advance this LSTM by giving it an input vector for the next time, right? And the vector that I give it is just going to depend on the operation. So we can do that by just doing scanner.add_inputs. We'll make some parameters for this. So let's say inputs. So basically, what's happening here is every operation is going to have its own vector. And I'm just going to look up that vector and put it into the LSTM based on the choice that I've made. And then I just pass this guy down. And I am done. This is my full definition of that model. Oh, well, I have to glue it together with the encoder. So we just need to fill in parse down here. I made the encoder return an LSTM scanner this time. Just make this faster. And this is actually the model that I showed you in the beginning of the talk. I only have 2 minutes, so I won't train it, but you can train it exactly the same way that you saw everything before. OK? So that's it for how we build this demo. OK, that's basically the end of the talk. Let me just summarize what I have talked about. So I've presented a Scala library for doing deep learning, or structured prediction with deep learning, deep neural networks. And our library is called Probabilistic Neural Programs, and it basically combines two interacting elements. It combines this representation of a structured output space, which is like a probability monad, with a representation for neural networks. And these two components can interact. So the neural networks define the probabilities of the output space, and the output space defines the architecture of the neural network. And I've shown you how we can use this for a variety of applications, like defining simple probability distributions to the sort of natural language calculator example that we just saw. That's it. I want to say if you have questions after the talk or something, you want to reach me on Twitter. I'm at Jayant Krish. Feel free to tweet at me. Also, we are recruiting at Microsoft Semantic Machines. If you thought this talk was interesting and you're interested in sort of natural language applications or whatever, please do come talk to me. We have a really excellent team of people, and we are hiring aggressively. So that's it. Thank you for your attention. I will take any questions.
Great. Thank you, Jay. Questions?
Yeah.
After your encoder, an encoder in natural language processing is not probabilistic. It results
Right.
in a deterministic vector. So how is it in the PNP? It's still a deterministic distribution?
Yeah, it is.
It's
So
just like a wrapper, like a monad pure operation that is just does not have any side effects.
yeah, so the question is, why does the encoder return a thing in a PNP? Because it's not a distribution.
Yeah.
And the reason it returns a thing in a PNP is because the PNP actually represents two things. It represents the probability distribution, and it also represents the dependence on the model parameters. So the encoder depends on the model parameters, even though it always returns the same thing.
So it's a mix of the expression tree and the probabilistic thing.
Yeah.
Mixed together in this one type.
Yeah, yeah.
So we're a little short on time, so
Yep.
let's thank Jan. Fascinating.